my great honor to introduce Professor Oleg Kochukhov from Uppsala University in Sweden. Professor Kochukhov does theoretical and observational research in several topics in stellar astrophysics. His scientific interests center around the problems of stellar activity and magnetism and their impact on exoplanets. He also studies non-radial positions in stars and works on determination of stellar fundamental parameters, atmospheric structure, and the chemical composition. Today, he is invited to give us a seminar about stellar magnetism for M-dwarfs. Okay, let's welcome Professor Kochukhov again, and we can start the seminar now.
Yes, thank you for this introduction. So now I'm sharing my slides, and I hope everyone can see them.
Yeah.
Yes, my research interests are fairly broad. Very generally, I do research on stellar activity and magnetism, but that concerns all types of stars, starting from early type O and B type stars and going all the way to the smallest stars there are, M-dwarfs. And actually, it is this later type of stars about which I would like to talk to you today. So, giant fields of small stars. This is roughly the overview of my talk today. I will very briefly introduce what are these M-dwarfs and why studying these stars is interesting. Maybe many of you might know that already, but still for those of you who are in solar physics, that could be interesting. I will very briefly describe what methods we are using to directly detect and characterize magnetic fields in stars, including M-dwarfs. And then I will talk about recent results of M-dwarf magnetic field studies. And I will split it into sections devoted to total magnetic field measurements from Zeeman broadening and intensification, and then studies of large-scale fields from polarized spectra and what are the trends and interesting results and puzzles that emerge from this. At the end, I will very briefly mention comparison between observational results, and theoretical dynamo models. I would like to mention that a lot of this material is based on my recent review article, which I published in Astronomy and Astrophysics Reviews earlier this year. This article is published in open access, so you can grab this QR code and immediately proceed to the PDF file of the paper if you are interested to learn more about this topic. So a few words about M-dwarfs. These are smallest stars with masses in actually a fairly large range. One doesn't realize often that the range of masses covered by M-dwarfs is like a factor of 5, and temperature is maybe a factor of 2. So they cover very substantial range of stellar parameters. And the hottest M-dwarfs are more similar to stars. Well, they're kind of similar to late K dwarfs, of course, whereas the lowest mass, the coolest M-dwarfs, are actually more akin to giant planets. So there is a tremendous range of parameters in terms of, let's say, dominant temperatures and densities and atmospheric conditions that are covered by these stars. M-dwarfs are also very common stars, at least around the sun, in the vicinity of the sun. They are faint in the optical wavelength domain, and their spectra are dominated by molecules. And the later the stars, the cooler the stars, the more intense are the molecular lines. And just to appreciate the degree of this effect of molecules, below you can see the plot of the spectral energy distribution of the sun and of the nearest system which hosts a planet similar to Earth, a rocky planet orbiting M-dwarf Proxima Centauri. So the spectra here, the spectral energy distributions are scaled according to radiation that planets receive, Earth and correspondingly Proxima and B receive at their distance from the star, and you can see how much the yellow spectrum compared to the black one is shifted to the red, and then is also affected by this massive absorption bands of different molecules, especially below 1 micron. Another interesting aspect of M-dwarfs is that their structure undergoes a significant transition at around 0.35 solar masses. So they switch from becoming partially convective, having a structure kind of similar to the sun, to fully convective for masses below this limit. And it is interesting to see whether this transition coincides with any changes in the activity properties of these stars, in the characteristics of their magnetic fields. M-dwarfs nowadays are extremely popular as exoplanet hosts, and in particular, their primary targets to detect and characterize atmospheres of rocky, small exoplanets located in the habitable zone. And there are obvious reasons for that. The M-dwarfs are significantly smaller in mass, radius, and luminosity compared to G-type stars, so it is much easier to detect variation in velocity or eclipse signature for an M-dwarf orbited by a rocky planet compared to the G-type star. And of course, such habitable exoplanets around M-dwarfs are located much closer to their host stars, so the periods are shorter, and we don't need to wait for the entire year in order to reobserve the eclipse or cover or obtain full phase coverage of radial velocities. So the periods are typically within a week or two. And the closest exoplanet systems containing rocky planets, such as Proxima Cen, such as Barnard's star, these are all systems having M-dwarf as a host. So it is a very significant research direction in exoplanet field nowadays to study M-dwarfs as exoplanet hosts. But at the same time, there are concerns to what extent the magnetic activity of M-dwarfs is influencing the properties of exoplanets, and maybe not allowing potentially biological life or complex chemistry develop on their surfaces. And there are various reasons how magnetic field of a star can influence exoplanets. This is not really my research field, but I'm mentioning a few possibilities. Direct influence of stellar winds that may strip atmospheres of exoplanets, that guide propagation of coronal mass ejection, that govern energy balance of planetary atmospheres, and even for stars with particularly stellar hosts with particularly strong magnetic fields, these fields are capable of melting the interiors of rocky planets, as was demonstrated in some theoretical studies. But the bottom line of this discussion is that we do have to obtain detailed information about both strength and geometry of the magnetic fields of exoplanet hosts in order to understand environments in which these exoplanets exist. And this is where my research comes in. Of course, even before we could directly measure magnetic fields on the surfaces of M-dwarfs, we had a lot of clues that these stars are probably strongly magnetic, probably having significant surface magnetic fields and spots. Well, we had, for example, evidence from photometric variability and from flares. And just to demonstrate how these phenomena can be observed these days, thanks to the TESS mission. Here is the typical light curve of one of the brightest M-dwarfs. You can see clearly sinusoidal modulation due to spots, large-scale spots, and on top of that, there are these spikes. These are flares of different magnitude and duration. Of course, similar to the sun and solar-type stars, the presence of activity, magnetic activity, is betrayed by chromospheric emission, calcium H and K lines, the H-alpha in emission, and even calcium infrared triplet lines in emission are all observed for active M-dwarfs, and increased X-ray emission as well. What is also interesting, and what was realized relatively recently, is that M-dwarfs, if they are plotted in this diagram, which is the ratio of X-ray to bolarimetric luminosity as a function of so-called Rossby number, the ratio of stellar rotation period to convective turnover time, they are indistinguishable from more massive stars. So in this plot, the colored symbols are fully convective M-dwarfs, so those stars that are less massive than 0.35 solar masses, so they must have fully convective interior, which is qualitatively different from the open symbols, partially convective stars. And despite that, they clearly follow more or less the same pattern of activity, with activity rising as the rotation of the star gets faster and then reaching the saturation level here. So maybe, even though we are looking at stars that are structurally different from the sun, we can actually learn something about dynamo in the sun, because apparently there is no difference in activity rotation relation for M-dwarfs. But that's all indirect evidence of the magnetic field. We still would like to obtain direct information. So how do we do it? Well, we use two manifestations of the Zeeman effect. As schematically illustrated here, if we have magnetic field present, then energy levels are becoming magnetically split according to their quantum numbers and according to the lambda factors of the levels, and that corresponds to splitting of spectral lines in the intensity spectra. In addition to that, if we are capable of measuring polarization in spectral lines, which requires quite specialized equipment, a combination of spectropolarimeter and spectrograph, then we can detect the circular and linear polarization in spectral lines. And based on this, we can quantify the entire, all three components of the magnetic field vector, not just measure the strength, but also to measure orientation of the magnetic field. And I will talk today about results obtained using these two different methods, polarimetry and Zeeman broadening using intensity spectra. Here is an example how magnetic field signatures may look like in these two different observables. On the left, you can see typical impact of magnetic field on the stock size spectra. So these are theoretical spectra that are plotted in the order of increasing magnetic field from 0 here to about 4 kilogauss. And you can see how the line becomes broader. And then on the right, you see Stokes V profile for, again, a range of magnetic fields. It is important to realize that when we are detecting magnetic fields using Zeeman broadening in Stokes I, then the effect is proportional to the absolute value of the magnetic field. So the broadening is linearly proportional to the field. But here we have to do a really detailed work to recognize relatively small contribution of the magnetic field on top of various other processes that produce broadening of stellar spectral lines. And because of this competition, the signatures of magnetic fields are very quickly washed out by turbulence, by rotation, and so on. So we can only detect with this method relatively strong fields. On the other hand, this method, looking at intensity spectra, gives us information about any field at any scale. It can be a very complex field. It can be structurally very simple field, like a dipole. We will still see it in the intensity spectra because intensity spectra are sensitive to the modulus of the magnetic field. When we look at polarization, the situation is quite different. First of all, polarization provides much more easily detectable or much less ambiguous signature of magnetic field, because we perfectly know the zero model. When magnetic field is absent, we have flat polarization. So any detection of polarization signifies the presence of the field. However, as is evident from this plot, polarization depends not on the absolute value, but on the orientation of the field. So in particular, in circular polarization, we measure the projection of the magnetic field on the line of sight. So basically, B times the cosine of the angle between magnetic field vector and line of sight. And because of that, the signatures in STOXV can have different sign. And therefore, as we average over the surface of the star, as we detect only the disintegrated signatures on Earth, there is a great deal of signal cancellation. So the field that we detect in STOXV is not the total field, but only the largest components, the simplest part of the field. And typically, we also require to have to carry out multi-line cross-correlation type of analysis in order to get to some signal over many spectral lines and detect the signature that can be quite weak sometimes. But if we do time series analysis of this signatures, we can reconstruct the full detailed vector map of the global field. So we're sensitive to weak fields, but only at fields, only to fields at larger scales. Here are practical examples of applying these two techniques. Not well, the left-hand side shows Zeeman broadening and intensification. In this case, this is applied to an active G-dwarf star, and you see 4 panels with lines having different lambda factors, meaning that they have different magnetic sensitivity. These lines come from the same multiplet, so we perfectly know their relative oscillator strength. There could be no ambiguity between magnetic intensification and non-magnetic line strength. And you can see that the line which has no sensitivity to the magnetic field is here, so it does not react to the field. And for the 3 other lines, we actually need to introduce the field of the order of 1.4 kilogauss in order to match the observed spectra, which are here with shown with black points. And if you look carefully at this line 5497, which incidentally is the most magnetically sensitive line in the spectra of G-dwarfs in the optical domain, this line you can actually also see magnetic broadening. So this line becomes stronger and becomes broader. And the right-hand plot illustrates an example of application of reconstruction of the global field from polarization. I'm not really planning to speak a lot about the methodology. It is suffice to say that we have a time series of polarization profiles shown here in this column. And then there is an inversion code which fits some combination of surface spherical harmonic modes that reproduces these observations under additional assumptions of simplicity. So we're trying to reproduce observations with as simple field structures as possible. So this is methodology. So what are the results of applying this methodology to M-dwarfs? Well, first of all, I have to, of course, acknowledge early work on M-dwarfs that was done in the late 90s and early 2000s. So there were a few papers actually even in the 80s where for at least one star, AD Leo, the brightest M-dwarf, a clear magnetic splitting corresponding to a field of around 3 kilogauss was detected in the infrared by Saar and Linsky. And then later on, Valenzi and John Skrull have used a red iron 1 line to demonstrate the presence of the field in EV-LAC, a famous active M-dwarf. And looking at this plot, you can kind of see all the complexity that is associated with this analysis. So what you are seeing here is the spectrum of an active star in black compared to the sequence of inactive template stars, so stars with known spectral types. And the magnetically sensitive line is here in the center, and the surrounding lines belong to titanium oxide, which is not magnetically sensitive, at least not here, not in this wavelength region. And you can see that titanium oxide sort of matches quite well. There is good agreement between active and inactive stars, but this iron 1 line is significantly broadened and maybe even split in EV-LAC compared to inactive stars. But extracting any quantitative information about magnetic field in this case is extremely difficult because of this blending by titanium oxide and other molecular features. Later on, there was also another technique which was developed, well, suggested by Valenti, but then later developed by Reiners and Basri, where they essentially matched the observations of active M-dwarfs and even brown dwarfs with a superposition of linear superposition of active and inactive template spectra, which were broadened to account for rotation and which were assumed to have known magnetic fields, basically from analysis of Jones Krull of Valenti, but that allowed to analyze a lot of stars with relatively low precision of about 1 kilogauss. So for a while, the research area has kind of stagnated. We knew about a couple of stars with fairly strong fields up to 4 kilogauss, and we couldn't measure stronger fields because of this difficulty of interpreting spectra blended with molecular features. But then it turned out that there is a very nice region located close to 1 micron that was largely overlooked by the community. And it was overlooked because this region was affected by telluric absorption lines and considered to be not usable. But modern methods of modeling telluric absorption in stellar spectra are sophisticated enough to allow us to remove very accurately these telluric lines. And there is a group of titanium-1 lines from, again, the same multiplet, so their relative oscillator strength perfectly known, close to 1 micron, which in many M-dwarfs show really clear signatures of magnetic broadening. And very fortunately for us, one of those lines turned out to have also 0 Landau factor. So one line is magnetically insensitive, and you can see this line here. So this plot is similar to what was shown before. So the observations are in black. The dashed line corresponds to non-magnetic spectrum, and the solid red line corresponds to the spectrum, theoretical spectrum, including magnetic field. In addition, near to these titanium lines, there is iron hydride lines, so the same lines that were modeled by Reiners and Basri, but the advantage here, or the progress that has been made here, is that we learned how to calculate magnetic field effects in iron hydride lines from first principles. So we actually can do spectrum synthesis incorporating rather complex physics of Zeeman effect in molecules. And so for the same star, you see similar comparisons. So these plots show quite convincingly that that particular star, WXMR, is having as average field of 7 kilogauss. Moreover, with this methodology, with this kind of observations, we are not only able to derive some kind of mean field, typical field, but we are able to fit the distribution of the magnetic field strength, this kind of histogram as illustrated here. So we usually split magnetic field in different bins of 2 kilogauss, 1 kilogauss, and then allow computer codes to find filling factors corresponding to these different bins of magnetic field strength. And those titanium lines also provide excellent diagnostics for rapidly rotating stars, which were previously not studied at all because it was assumed that you can only do Zeeman broadening on slowly rotating stars because you want to see how the lines are broadened. But if you use instead Zeeman intensification, if you focus analysis on measuring magnetic effects on the line strength rather than line width, there is no reason why you cannot apply magnetic diagnostics to very rapidly rotating stars. In fact, we have succeeded going up to VSI values of 40, 50 kilometers per second. So this is one example of how, of the evidence of magnetic field in a fairly rapidly rotating, I think it's the primary component of this famous M-dwarf eclipsing binary YY gem. So observations here are with symbols. And again, the dashed line without magnetic field and the solid red line shows this theoretical spectrum that matches observations, including this value of magnetic field, 3.4 kilogauss. And so, thanks to this recent progress, 4 or 5 or 6 papers of that order of magnitude, we now have, instead of half a dozen stars, something like 62 stars, M-Dwarf stars with accurately measured magnetic field strength, measured using this modern techniques of fitting theoretical spectra to observations of titanium-1 lines and iron hydride lines. And this is my attempt to summarize these results by plotting average magnetic field strength as a function of Rossby number, more or less this rotation activity diagram, but now using direct measurement of magnetic field as opposed to proxies. And well, you can kind of see that there is a rising branch of this activity relation. It's not easy to say whether or not where the saturation regime starts. There are quite many stars now with very strong average magnetic fields. 4 stars with fields stronger than 6 kilogauss, and I think more than a dozen stars with fields as stronger than 5 kilogauss. You can see that at the same Rossby number, there is often a significant spread of points in this diagram, and this scatter appears to be real. It's really the case that stars with identical mass and identical rotation period can have a very large difference in the average magnetic fields. And what is even more interesting to note is that there seems to be, let's say, correlation between the strongest total fields and the topology of the large-scale magnetic fields, about which we will talk later, the results of polarization analysis. So the stars with the strongest fields, basically stars located here, are all having axisymmetric dipolar global field geometries. Maybe that tells us something about underlying dynamo mechanism. Now, what are the results obtained from polarimetry? So here, this is, well, let's say, typical example of such analysis. There are recordings, observations of polarization obtained for an M-Dwarf, in this case, AD Leo. Then to these observations, people apply a cross-correlation technique that combines signals from many different spectral lines, in fact, thousands of spectral lines, that gives so-called least squares deconvolved, or LSD, average polarization profile. And then this average polarization profile is modeled using some rather simple assumptions about line formation physics. Very often people use Milne-Eglinton models, analytical solutions, or even weak field approximation, which is a bit questionable maybe in this case, because the fields are not, well, at least some components of the fields are not necessarily weak. So generally, it turns out that there are 2 kinds of magnetic field, global magnetic field topologies, large-scale magnetic field topologies that polarization information provides. So there are stars like AD Leo in this case with relatively strong and axisymmetric fields, and these fields seem to be quite stable. So these are, for example, observations from 2 consecutive years, and both observations show the same structure of magnetic field. So in this magnetic field maps, what you are looking at is the flattened polar projection of the magnetic field. So we are looking at the star from the rotation pole, and this column corresponds to the radial field, azimuthal field, and meridional field. So this is one type of field that is being detected. Another type of field that is being detected is a bit weaker field and with more complexity, and also possibly some evolution from one year to the next. So this is another example of an M-Dwarf observed in 2 consecutive years. You can again see magnetic field maps, and you can well suspect that there is a difference between these 2 maps. what you can realize if you look carefully at the actual numbers that are printed here, 0.19 kilogauss, 140 gauss in here, this field strength that we see in polarization are significantly weaker, orders of magnitude weaker than what Stock psi tells us. And this is the consequence of cancellation of different field polarities in the polarization diagnostics. You can imagine the star having different components, different magnetic spots that are still arranged in some kind of global dipolar configuration, but polarization signals from these spots produce Stokes V profiles with opposite signs. And when they are added together during disk integration, significant part of the polarization signal vanishes. So it's nice to have maps, but the strength here is very much underestimated. The results of this ZMM Doppler imaging mapping of global magnetic field topologies are available for about 3 stars or so, 30 M-dwarfs. And in this research area, we usually plot the results in this diagram, where we have information about the mass in y-axis, information about the rotation period or Rossby number in the horizontal axis, and then other properties of magnetic field are encoded here as the size of the symbol, which corresponds to the field strength, and then the shape of the symbol corresponds to the axis symmetry of the field. So roundish symbols are fields similar to this type of field, the axis symmetric field, whereas this star would have a star-like symbol. And so there is definitely a trend here in the sense that we find stronger global fields in fully convective stars. So this dashed line corresponds to the limit of fully convective interior. And there also seems to be a peculiar behavior in here for the lowest masses, because again, stars of the same rotation period and the same mass exhibit dramatically different global field topologies. So there is some kind of dichotomy at the lowest masses. And one can perhaps speculate that maybe such stars have been born in a different environment, evolved differently. But curiously, this type of dichotomy has been demonstrated even for M-dwarfs that are members of binary systems, wide binary systems. So these stars, for example, this pair, BL and UV Ceti, have been born together. They have the same age. And as you can see from the parameters given here, they have very similar masses. Masses are known because they're in a binary system, so the orbit can be traced and masses can be measured. They have nearly identical rotation periods. And yet, from these plots of magnetic field maps, global magnetic field maps, you can see how the secondary component, UV Ceti, has much stronger and much simpler dipolar-like magnetic field compared to weaker and more complex field of primary component, BL Ceti. So we think that this dichotomy is real. We think that it tells us that results of the dynamo in these stars are not a simple function of rotation rate and mass of the stars. Something else is at play.
Oleg,
there is a question, yes?
What about planets in these stars? There may be the reason for that?
Well, I mentioned in the beginning that it is in general interesting to study M-dwarfs because of planets. I think for these stars with magnetic field maps, we do have now information about magnetic field of Proxima Cen, which is here on the plot, as you can see. And I think we also have, we can say we have information about AU MIG. So yes, We do have maps of exoplanet hosts.
What I mean is, could planets be the reason for the dichotomy?
No, we don't think so, because at least as part of this Doppler imaging analysis, we do calculate average profiles, and we do try to measure radial velocities with sufficient precision to detect planets. So I'm not aware of any dichotomy related to the presence of planets in this case.
Mm-hmm. Thanks.
Yeah, but I think this cannot be really excluded. Maybe one needs to look deeper into that. One thing I also would like to mention while we are on this page is that what you can see maybe quite clearly, that there is a huge unexplored parameter range corresponding to more slowly rotating M-dwarfs. So Proxima Cen and a couple of other stars, but then we know very little about stars with rotation periods of a few months, for example, and that is directly related to the difficulty of obtaining observational data. It's much easier to observe stars with short rotation periods, like all those objects. So if we try to bring together information about global magnetic field and the total magnetic field, so global field from polarimetry, total field from Zeeman broadening and intensification, then what we can say is that the global magnetic field accounts for a very small fraction of the total magnetic field energy. So here I'm plotting the average, the ratio of the average global field. So this BV is the global field, and this is divided by the total field strength from Stokes I, and this is plotted as a function of mass. And then stars with simple dipolar-like global magnetic fields, axisymmetric fields, stars that are in this diagram shown with round symbols, with circles, are these red symbols. And then squares correspond, blue squares correspond to stars with weaker and more complex global fields. So there seems to be some kind of trend here. Again, the global axisymmetric field rise roughly at the stage when the stars become fully convective. Roughly at the boundary of full convection, we start getting this very strong axisymmetric fields. But then, as I said, the dichotomy is real. So at the same mass, we do have this group of stars with complex weak fields, and then we have other stars. And that is, let's say, similar ratio plotted as a function of total field strength. So if stars have stronger field, then there is a tendency of larger fraction of that field to be at large scales. So there is this trend as well. And so how can we understand, at least visually, if not from first principles, visually, how can we understand the structure of M-dwarf magnetic field? So maybe we can imagine that we have a carpet of very complex magnetic spots, something like that. And then this is superimposed onto a large scale field, something like that maybe. So the superposition looks like this. And this carpet is much stronger than the smooth field. And using this approach, I actually tried recently to model observations of stars, a few stars with very strong and axisymmetric magnetic field, switching from rather simplistic modeling of mean line profiles, that was the usual procedure in Zeeman Doppler imaging until now, to actual detailed modeling of individual line profiles using full polarized radiative transfer methodology. And it is indeed possible to reproduce both Stokes V profiles and Stokes I profiles of these stars, selected stars, using some parameterized model that is basically, well, I have some distribution of field strength here and assuming random field, and then I have a dipole, axisymmetric dipole here. So this is the comparison of observations and one of these models. So I don't really want to go into great detail in explaining this, but the message is perhaps this understanding of magnetic field of M-dwarfs is not very far from reality. Very often a question comes up about what can we say about magnetic cycles of M-dwarfs. And there is a lot of research that is carried out trying to find magnetic cycles from classical indirect diagnostics, such as X-ray emission plotted as a function of time, calcium emission, K emission plotted as a function of time. And it has been suggested that certain M-dwarfs have cycles of typically, well, comparable to the sun, maybe 5 to 10 years. And one of these suggestions is illustrated here. So in this case, I think it's for AD Leo. Yeah, AD Leo, calcium emission, K emission plotted as a function of time, and there seems to be a sinusoidal behavior with a period of 7 years. But what is puzzling is that when we look at the magnetic field measurements, we don't really see any evidence of cycles. So for example, for this star, AD Leo, again, at least it has been measured since 1985. That's the first star in which Sar and Linsky discovered Zeeman splitting in infrared spectral lines. And it has really the same 3.1 or 3.0 kilogauss average field that is staying very, very stable. So we have maybe 15 or so measurements spread over 30 years, and this scatter is plus minus 0.1 kilogauss. If we look at the polarization profiles of this star, it shows a non-reversing global field topology. So this is the sequence of mean polarization profiles. We were a little bit excited in 2016 when we got this data set, which hinted at the reduction of the amplitude of the polarization signature, and we were hoping that maybe the star is going to flip its magnetic field, so we can claim the detection of magnetic cycle from the global magnetic field diagnostic. But no, the star just returned to its previous state. So at least from direct field measurements, we can rule out short cycles. So there is no cycles on time scales of 14 to 30 years for this star and other stars that have been measured repeatedly. A few words about dynamo models. It's extremely interesting and productive research area because apparently it's very easy to calculate magnetic field generation in the fully convective stars. Well, I guess it's because the structure of fully convective sphere is easier to approximate compared to partly convective interior of solar-like stars. So there is no shortage of theoretical models that have been proposed, but there is still no convergence, I would say, in the sense that the global and small-scale magnetic structures suggested by those models are quite diverse and not always compare favorably with observations that are available. But among those models, I can maybe highlight anelastic spherical harmonics simulations by Gastini and collaborators, who actually managed in their dynamo models to obtain bimodality, let's say, of the dynamo solutions. And that was claimed to be an explanation, a possible explanation of two types of magnetic fields that are observed for low mass M-dwarfs. So you can see here you have a roughly dipolar strong field, and the plot below has the complex field. And these are not phases in the magnetic cycle of the same star. These are really more or less stationary dynamo solutions that in their simulations persisted forever. perhaps one of the most detailed and the most the model that was tested in greatest detail against observations was the simulation by Yadav and collaborators from 2015. And they just computed a single model with rotation period of 20 days, so still a bit longer than typical active M-Dwarf. But what they got is illustrated here. So this is the full resolution of their simulation, radial, meridional, and azimuthal field. And you kind of see something similar to my empirical model. So there are a lot of small-scale structures, but at the same time, those small-scale structures tend to be arranged in some kind of global magnetic field distribution. Of course, when we perform polarimetric observations, we do not resolve this small-scale detail. We get a field like that. So this is the low-pass filtered image corresponding to full resolution map here. And it was also demonstrated that if these data are used to produce simulated observations, and then the inversion technique, the global magnetic field mapping technique, has been used to recover back distribution, well, one gets a sensible reproduction. At least we can recognize that this is the star with a predominantly dipolar global magnetic field. But notice how much magnetic field we are losing. So here the range is from minus to plus 3 kilogauss, but here the range is from -8 to +8 kilogauss. So there is a lot of small scale structure that becomes invisible in polarimetric observables. All right, so this is essentially all I wanted to cover today. And here is a brief summary, the most important messages that I would like to convey in my talk. It is kind of curious that among the cool stars, late type stars, M-dwarfs are the most magnetized stars, with average field strength reaching now 7 kilogauss for the record holder. And it's certainly not a unique star. There is a handful with 6.5, 6 kilogauss. And remember, we are talking about really close stars. All of these stars are within a few tens of parsecs from the sun because they're so dim. They cannot be studied further away. So it is fairly easy to imagine that if we would build a larger telescope, if we would equip next generation large telescopes with spectropolarimeters capable of doing this type of analysis, we would discover M-dwarfs with fields in excess of 10 kilogauss, maybe 10, 15 kilogauss. And this is average field, remember. So there is still a distribution of field strength on the surface of the star, and the strong field tail of this distribution goes to maybe 20 kilogauss or so. So these are very interesting environments from the stellar physics perspective. It seems that observations can be interpreted by the superposition of weak large-scale field and strong small-scale field components. As we decrease stellar mass, it is more common to find M-dwarfs with more ordered global magnetic fields with its axisymmetric stable dipolar fields. But at the same time, we do have this interesting conundrum that stars with similar mass and rotation rates are having different magnetic properties. So the dynamo does not have a unique solution in a way. That's a bad message, but news for our ability to predict impact of magnetic field on individual host stars, exoplanet host stars, because basically means that I cannot provide you with some kind of simple relation, scaling relation, that you plug in some simple observable calcium emission, K emission measure and get out the magnetic field strength. No, it's really necessary to investigate in detail magnetic field strength in geometry for individual exoplanet host stars. But there are new instruments that are coming online, in particular in the infrared, near-infrared, with Spiro at CFHT and Criris at VLT. These are high-resolution instruments equipped with polarimetric devices. And thanks to these instruments, we are expecting hopefully very quick and dramatic progress in our understanding of M-Dwarf magnetic fields in the near future. So thank you.
Thank you, Oleg. Questions? Anyone, if you have questions, please raise your hand. I see a few hands raised already. So maybe John first.
You mean me, or?
Yeah, yeah.
Hello, Jörn.
Hi, Oleg. So first of all, thank you for the very nice talk. And so you should blame me and Gustavo. We were actually, it's our fault that you have to give a talk here so late in the evening for us.
It's okay.
Late in the evening. But yeah, thank you. Very, very interesting. So to maybe to summarize, so one idea was also to invite you to say, is there evidence if the tachocline is important or not? So if you see a clear difference between fully convective stars and partially convective stars. And if I understand it correctly from your talk, there is some kind of a difference, but it's not really so clear. Or
the greatest difference I see is perhaps in this diagram, where the boundary of fully convective interior corresponds to the moment when we are starting getting some kind of global, well-ordered, strong magnetic fields. So you can see that larger roundish symbols, and round here corresponds to axisymmetric fields, really start to appear around the fully convective boundary. So maybe that's the only trend that we see. But okay, the other trend I would say it's also the field strength. So the stars with the strongest field are also found. The strongest total field are also typically found among lower mass stars.
And maybe related to this, you said exactly in this plot, you see that you even for the same mass of this one, for the same mass, you see the different kinds of field strengths, but also field topologies. Could it be? I mean, that's also more speculation. That maybe that is kind of one dynamo, but it has just very long-term phases, and you just look at the stars, basically, you know, in the kind of minimum or kind of maximum.
Yeah. So of course, it cannot be excluded that stars do things while we are not looking. So if the stars have activity periods 200 years, there is no way we could kind of
I think
judge
we should,
that.
As a comment, I think we are a bit spoiled by that the solar cycle is so nice regular. I think this is normally not the case for other stars, or so it could be that in M-Dwarf it is very complex, and you have really these long-term behavior.
I should say maybe that some of the dynamo solutions. So there was another paper by Yadav where they calculated dynamo models for significantly slower rotating stars than the model that I illustrated here. They calculated the model for actually Proxima Cen with, I think, 90 days rotation period. And in that model, they actually got nicely periodic solution with a cycle of around 10 years.
Yeah, I mean, just a comment to this. I mean, what Rakesh got in these models, that is actually not that different what lots of other people would get with partly convective stars. So the solution are actually very similar. We don't see actually much, and that's also what you showed, what Petri's recent simulation, Petri Capules, show that actually we don't see much of a difference, at least in the parameter space we can do, between fully convective and partially convective stars.
Yep.
Okay, and maybe Irina next.
Hi, Oleg. Thank you very much for interesting talk. I have more, I would say, technical question. During your presentation, you show like synthetic modeling of Stokes profiles, right? But to compute them, you need to have absolute abundances. And it looks like it is a big problem. What kind of absolute abundance you have to use to make proper calculations of Stokes profiles?
No, I wouldn't say that this is a problem. So, well, just looking at this plot, for example, what we are having here is a set of spectral lines belonging to the same ion, to titanium, neutral titanium. One of these lines, this one, is magnetically insensitive, so it can be employed to determine abundance. So abundance is always a free parameter in this kind of plots, and it is uniquely determined. It is not ambiguous, because we're dealing with lines that have very different response to the magnetic field. So its abundances are not a problem.
Okay, is it any correlation between like relative abundances and the absolute one?
Sorry, I don't really understand what are relative abundance.
My question is if it is any way to estimate more precisely this from relative abundances, just this.
Well, okay, so that's sort of kind of a separate story of how we can use M-dwarfs to learn about stellar abundance and whether we can reliably extract absolute abundances from M-dwarfs. This is difficult, but not because of, well, it's difficult because we need to have a very detailed understanding of chemical reactions that are occurring in the atmospheres of M-dwarfs. But remember, all these M-dwarfs that we can observe and model, they are relatively close to the solar system. They are in our neighborhood. So in this sample of stars, we don't really have a representation of these different stellar population, thick disk, thin disk. These are all our neighbors. So they all have abundances in relatively narrow range around the sun. So they are not so useful in kind of galactic context, in the context of looking at different stellar populations, just because they are so near.
Okay.
That's our backyard, so to speak.
Okay, maybe Shudong next. We have a few more raised hands.
Oleg, thank you for the nice talk. So I'm really intrigued by this 6 to 9 kilogauss M-dwarfs. The field seems very, very strong. And I'm just very confused by the formation mechanism, like the flux tubes that emerge on the stellar surface, right? Are they emerged like, you know, as 10 kilogauss small scale field? In that sense, it seems to be randomly distributed and wouldn't form such a nice dipolar structure. And on the other hand, if it's like the solar case, right, region, black to region, and towards the post, then does that mean that you know, stars would produce huge star spots with 10 kilogauss fields? You know, that's just very intriguing to me. Do you have any comments?
These are all very, very good questions, and I don't have really good answers to most of them. Perhaps what I can say is that we don't really have evidence, observational evidence, for massive, large-scale spots with strong field. So we think that this strong fields are distributed more or less homogeneously over the surface of the star. And how do we know that? We know that because the non-polarized diagnostics, those lines, for example, of titanium that display evidence of magnetic broadening and intensification, if we perform time series analysis of those lines, we don't really see a lot of time dependence. So if we look at the star from different aspect angles, we see the same broadening. So there is very little modulation, unlike for the Stokes V, at least for some stars, which means that if these very strong fields are concentrated in spots, these spots must be very, very small and distributed rather homogeneously. how exactly it looks at the surface of the star, what kind of multi-atmospheric multiple components we have for the atmosphere, I really cannot say. So I'm hoping that theoretical simulations would inform me about this.
Thank you.
Okay, maybe Alfio next.
Okay, thank you, Oleg, for your nice talk. I have, let's say, a comment and question. The comment is the following. It seems to me that for your technique, you need to have structures which last long enough in the surface. So structure which lives more than the rotational period. So, for instance, you discuss AD Leonis, but AD Leonis is a rotational period of 2.2 days, something like that. So I'm not sure we can learn something about the solar dynamo today. We might learn something about how was the dynamo in the sun when the sun was young, and that is definitely a very important question to ask. But I have doubts that we can really detect cycles as we see in the sun, where usually the lifetime of spots is much smaller than the solar cycle with your technique. So I will be very skeptical on that. Can you comment on this?
Sorry, that's a talk about M-Dwarfs. I'm not really claiming anything about solar type stars. So of course you're right. So
no, you just did not mention any limitation about your technique, about the rotation. I mean, is it true? No, you need to have structure in the surface which lives longer than the period of the star.
Absolutely, yes.
Okay.
That's
that was
about these results.
No, just wanted to point out that this is, I would say, this is a basic limitation of the method. If one wants to learn something about tachycline of dichotomy of solar light stars of the case of the sun.
Well, yes and no, of course. So if you look in the literature, this type of technique of studying global magnetic fields with Zeeman Doppler imaging has been applied to solar twins, and some results were obtained. So it's not like there is no information at all. It just means that applying this technique to solar type stars, we are probing a very specific, the largest scale component of the solar magnetic field. So it is still interesting, but very narrow.
Sure, I'm not saying it's not interesting. I'm saying that there is an important limitation that one has to stress. Otherwise, it's difficult to understand the physical implication of that. For instance, one might see that there is a cycle produced by smaller scale, and you can just, because of the lifetime of the structure is smaller than the rotational period, we might not see that. We need photometry. That's my point. We also need photometry.
Well, just to give you a visual impression from one of my backup slides of what we are looking after, what we are looking for, we would like to have observations something like this. So this is not a solar type star, but it's a bit closer to the sun compared to M-dwarfs that I have discussed. So this is I think it's a K-dwarf, 61 Sig. And you see here the sequence of the radial field component, again, viewed from the pole of the star. And years are written below the maps. And you see that the star really changes from a simple dipole field to something complex. And then it changes the sign of the field on the northern pole. And that correlates very well with the intensity of the X-ray emission from this star. So we do have examples of stars that behave just the sun, like the sun. And these results were obtained with the same Zeeman Doppler imaging technique as I was discussing. So,
okay, thank you. I'm not just saying, as I said, I'm not saying it's useless, of course. It's very important. Just wanted to point out that we have to be careful in making inference on that. That's
Yeah,
only my
absolutely.
point.
So, Leif, please.
Yeah, that's a very interesting talk. My question was partly answered by the previous requester, but I will ask it again. Is there a similar type study or set of observations for solar type stars? In particularly, there was an old study from Mark Wilson that showed that some percentage, 10% or 30% or something, were in maybe a Maunder minimum type situation. It would seem to me that similar results might be obtained by your method here on other solar type stars. There should be a lot of them, so we should be able to get really good statistics on it. So what's the deal here?
Yes, there are studies of solar type stars. Well, this is one example that I'm showing here. There is maybe a few dozen, or at least a dozen of solar type stars for which this kind of maps have been reconstructed. It is still not as easy as one would hope to obtain these maps because of the rotation periods of these stars and the necessity to observe stars at different epochs, at different phases of their activity cycle. So this is tremendous investment of research time and research efforts. And also another limitation is that polarimeters that are capable of producing the or collecting required observational data are available on a very small number of telescopes around the world. So there is like 3 or 4 telescopes where you can obtain this kind of observations.
Okay.
So it is possible technically, but it's a question of resources essentially.
All right, thank you.
Okay, Gustavo.
Hi. Oleg, can you say something about differential rotation in the stars where you have measured the magnetic field? I know that for T Tauri stars, it's possible to get to infer some results about that.
Mm-hmm. So I didn't mention differential rotation at all here, basically for the reason that there is no unambiguous detection of differential rotation on M-dwarfs to the best of my knowledge. And there is overall understanding, I think I could call it consensus, that differential rotation decreases with stellar mass. So the stars that exhibit the largest degree of differential rotation are early G-type stars and F-type stars. And then as we go down in mass to K-dwarfs and then to M-dwarfs, any evidence of differential rotation disappears. I'm talking now, just to clarify that, I'm talking about latitudinal differential rotation that we can observe on the stellar surface.
All right. So yeah, just a comment regarding the previous question. I saw recently results from Julian David Alvarado about iota orology, and he's able to build a butterfly diagram based on CDI observations, which is an F star, rather similar to the sun, or at least similar than M-Dwarf. And also thank you for the nice talk.
Thank you for listening.
Okay, I guess. Okay. Last question from Travis.
Hello, Travis.
Travis, do you have a problem? Oh, okay, you're turned on. Okay.
I just wonder if you can comment on the.
Your voice is really low.
I cannot really hear at all. what Travis is asking?
Yeah, I heard you speaking, but your voice is really low now. Maybe you can type. Sorry about that. Oh, Travis has asked in the chat. So he asked Oleg to comment on the effect of age.
I would not dare to. So, okay, so let me unpack this a little bit. Of course, we do expect M-dwarfs that are more active and more rapidly rotating to also be younger. However, to the best of my knowledge, but that's really your field, Travis, to the best of my knowledge, the age activity rotation relations are not really so well calibrated for M-dwarfs. And we also understand that M-dwarfs continue to be active much further in the evolutionary stage. So even relatively old M-dwarfs, like let's say middle-aged M-dwarfs, can be still active. And the fraction of active M-dwarfs tends to increase with decreasing mass. So at early M-types, it's relatively small fraction, maybe 10% in the solar neighborhood or so. But as we reach, I think, M5, we are up to 50%. So 50% of all M-dwarfs can be classified as active in terms of, let's say, emission, X-ray emission, and calcium K emission. So they slow down, they lose their activity much slower than solar type stars.
I think I figured out my microphone situation. Can you hear me now?
Yes, now I can hear you.
Okay. I guess my main point is that the sort of dichotomy that you see in the M-dwarfs is also seen in young clusters, where you have this dichotomy between sort of M-dwarfs that are still in the saturated regime and those that have already converged onto the spin down sequence, right? And so it may be a transition in their dynamos at young ages that leads to this dichotomy. That was my sort of supposition.
But would it still mean that these stars on different branches, as you say, they still have the same rotation period, right? That's what you're saying.
Yeah, they can have the same rotation and even the same mass, but their dynamos have flipped between states. Yeah, so I think others have kind of alluded to this solution.
Yeah, that's a possibility, certainly.
Okay, we are running a little bit over time. So if no more questions, let's thank Oleg again, especially so much interesting discussions and questions after the seminar. So we really appreciate your talk. It's very interesting and nice talk. So thanks to the speaker again, and same as before, the recording of the seminar will be put online at our websites after this talk. So anyone are welcome to.
Thanks for inviting me. Yes, and it was a pleasure to give a talk, and thanks for interesting discussion. They were nice questions.
Thank you. So I can call it now for the seminar. So let's meet maybe next month.
Okay, goodbye, everyone.
Bye.
Thank you.
Thank you, bye.
Bye-bye.
Thank you.